Hi, and welcome to PlasmaCon 2023. And thank you for joining my session where I'll be covering a solution for multi-cluster management in Kubernetes. My name is Tzachi Duek, and I'm a principal solution architect for containers at AWS. A bit about myself. I'm 20 years in the tech industry and more than 2.5 years in AWS. In my role, I'm acting as a field CTO for containers technology, working primarily with startup customers across EMEA. And if I wasn't in tech, I would probably dive deeper in mathematics. Our agenda for today is going to start with multi-cluster challenges for Kubernetes. Then I'm going to cover two of the building blocks of the proposed solutions, which are infrastructure as code compositions and GitOps for accelerated deployment. Then I'm going to cover the solution and share the resources with you so you can start using it today. So let's start with the challenges. And it usually happens when we choose Kubernetes as our container orchestrator. That leads us to the question of now what? What tooling and configuration should I use to run production workloads in my cluster? In the next couple of slides, I will cover the challenges you might face in your journey when you adopt Kubernetes. And as always, we start with documentation. We understand every bit of the system, every component of it. We get the flexibility, the benefit, and the feature it provides. But soon after, we realize it also involves complexity in provisioning, upgrading, and securing the cluster itself. This means we need to ensure we have a proper lifecycle management process for our control plane and data plane. For data plane, we have mechanisms such as node groups, which are a set of nodes that are managed by a controller. Usually it will be the cluster autoscaler. With Amazon EKS, for example, you can create and manage those node groups as part of the cluster creation process. However, it does not end up here. As the next step, we need to decide which cluster-wide add-ons we would use. The Kubernetes ecosystem has so many tooling to offer that it can become challenging to decide which add-ons we need to use. But even when we decide which add-on we would use, we still need to ensure we have a consistent way to deploy, manage the complete lifecycle of those add-ons. As a next step, we need to support multi-tenancy. That means that we need to define operational standards to support multiple teams and to deploy multiple applications. We achieve the separation between application in the form of namespaces. Within each namespace, we can define permissions for our application using service accounts. We can also limit the resource consumptions by applying resource quotas to all of those namespaces. There are, of course, other mechanisms that allows us to apply standards in our environments, such as limit ranges, pod security standards, and network policies. And as a last step, we should provide a scoped access control to those namespaces based on team responsibilities. As a final step, we would want to automate the creation of those clusters with all of their configuration across environments in a single pipeline with everything we discussed so far. We'd like to use the infrastructure as code tooling to programmatically describe the configuration. And this is where infrastructure as code compositions plays a key role in defining those standards. It allows platform builders to define high-level abstractions while ensuring standards and best practices are built into those abstractions. Those composition has different terminology in different infrastructure as code tooling, but they all means the same. In this session, I'm going to cover AWS CDK and HashiCorp Terraform as the infrastructure as code tooling. And as you can see on the screen, I took it from the documentation side of any of those tooling. In AWS CDK, those infrastructure as code composition simply called composition, while in Terraform, it's called modules. But again, their meaning is the same. These are just an example of those compositions to create and manage Amazon EKS clusters using infrastructure as code. Within each composition, there are configuration for both the service itself and its integration with other services, such as Amazon EC2 auto-scanning group that supports the node group for our control plane. So far, having the cluster configuration in place is great, but the main thing that provide business values is the business applications. And this is where GitOps gets in. But before connecting GitOps to the complete proposed solution, let's first define what GitOps means. We will look at the standards established by the CNCF GitOps Working Group. They define four principles. That means that GitOps should have a declarative configuration, which is stored in a version and immutable system that is pulled automatically upon merge or commit and continuously reconcile to the desired state. Before moving forward, let's discuss about GitOps topologies. The first one is sometimes called the centralized management topologies. With this topology, we have a single GitOps instance that manages all target environments that are usually remote to the system. The advantages of these topologies are that we need to manage a single GitOps instance. We also have a centralized access for all of our users to basically log into the GitOps instance. It can also be integrated with existing and remote clusters without configuring GitOps tooling on them. Don't need to change anything on those clusters. The challenges are that it can become really challenging to configure it on scales of tens and hundreds of clusters, as we need to support all of those clusters. The cluster creation process is not atomic, meaning we need to register, we need to do a post creation actions on those clusters to register it in this single GitOps instance. From security standpoint, we have a central instance that has a privileged access to all of our remote clusters. And we need to ensure we have the network connectivity because a single GitOps instance, as I said, that it needs to be able to reach out and reconcile all of the remote clusters. Other topology is sometimes called a standalone or a distributed GitOps. In this scenario, each cluster has its own GitOps instance deployed inside the cluster, which points to the remote repository. In the solution I'll discuss later, this topology allows to create a consistent cluster across multiple environments with GitOps tooling Bootstrap as part of the cluster creation. It allows us to achieve isolation as there's no single point of access to all the other environment. And infrastructure creation process in this case is atomic. We don't need to do any post creation action or scripts to register the clusters. The challenges are in user access. It can become challenging to log in to the specific GitOps instance if you want to observe something or see or log in into any of those instances in case of incident or something. And upgrade and updates, we need to ensure we have proper add-ons and lifecycle management process for add-ons and the GitOps tooling itself. Now heading over the solution. The solution today uses EKS Blueprint, which is an infrastructure as code composition we discussed earlier. EKS Blueprint is a project we released last year that supports both AWS CDK and HashiCorp Terraform and allows you to create a consistent EKS clusters across multiple environments. EKS Blueprint has three layers. The first layer is the cluster and the compute capacity. This includes the Amazon EKS cluster configuration as well as data plane configuration, whether it's AWS Fargate, Amazon EC2, Amazon EKS managed node groups, Carpenter, or any other combination of them. The second layer is the add-ons. EKS blueprints provide a complete lifecycle management for add-ons with best practices defaults built in. It also includes AWS-specific add-ons, community add-ons, and allow third parties to extend the framework to create their own set of add-ons. And as a last layer, EKS Blueprint includes access and permission management for users, roles, and group. This has been abstracted in the form of a construct called the team. A team definition is designed to provide a set of isolated boundaries between users and application that are configured and deployed in the same cluster. When you define an application, In application team using EKS blueprints, it creates the following. It creates the namespace for the application to be deployed into. It also creates the resource quotas for the application in those namespaces. Then it creates the IMO for service account with specific Kubernetes RBAC permission for that namespace. This role can only be assumed by the user or the role that is specified in the team construct. And last, it creates the IMO for service account can be used by the application deployed in this namespace to authenticate to other AWS services. In our solution, we use EKS blueprints to create a fully configured EKS clusters that are deployed across environments, to onboard multiple application teams in a consistent way across those environments. We also manage the cluster configuration and the pipeline definition itself using EKS Blueprint. The configuration is defined in a centralized repository called the Blueprint configuration. As you can see, the platform team are the one that owns the whole configuration of the cluster add-ons and the team themselves that deployed across all of those clusters. And as a last step, we provide a way to add new environment, but simply merging an updated infrastructure as code configuration to the configuration repository. In turn, the blueprint repository will update the pipeline automatically without you need to do any manual actions. From that moment, the pipeline will know the new environment and will treat it like as any other environment in the system. Following the team creation, we still need to onboard the application. This is where we use GitOps. In this process, the platform team onboard this new application using the tenancy model of Argo CD. This includes Argo CD definitions for projects and application. Argo CD projects constrain the cluster, namespace, and the Git repository that are allowed to be used for a specific application. Then, an application resource connects the Git repository to the target namespace of our deployment. This solution is covered in this blog post with detailed explanation of the design consideration we took when building it. You can also find a walkthrough and how to deploy it. You can either follow the solution blog post to deploy it or go directly to the source code of this repository. I'll pause here for a few moments so you can take a screenshot or copy the links, and I'll also share the links after the session. Thank you for listening. I hope this was useful for you. And if you have any kind of feedback or suggestion, please feel free to reach out to me on LinkedIn. You can either copy the link or scan the QR code, which leads to my LinkedIn profile. I'll be more than happy to hear your thoughts, feedback, or any other suggestion, as I said. Thank you.